Okay.
Perfect. So I think we have good number of participants who already joined. So welcome everybody. It's a great pleasure to have today Igor Balla, right, who made actually extraordinary effort to give this talk because when we agree with him, he's talking from California. It was supposed to be 1 o'clock in the morning California time, but then meanwhile time changed, so it's now 2 o'clock in the morning California time. So actually, right, we're very proud that Igor made such an effort to give a talk here, and we're looking forward to it. And he will talk about orthogonal representations, complexity of can you put back Igor there?
Sorry, I had a bit of an issue. Just give
I
me a
see.
second.
Yes. MaxCut orthonormal representation and extension complexity of polytopes. So perfect. So we're looking forward to it.
So thank you. Thanks for having me here. And indeed, I'm going to talk about a bunch of things. So there will be a good amount of definitions, but hopefully you'll bear with me through them because they're really not so complicated. And I think I want to tell the story of a bunch of things around this area. So let's begin. I guess we'll begin with question of Lovász, like as most things do, begin that way. So I guess in the 70s, Lovász asked the following question. Um, Suppose you have n unit vectors, and the question is, what is the maximum possible length of their sum if there are if they have the property that among any three vectors, at least one of the pairs is orthogonal. So of course, if there were no conditions, you could just have all the vectors point in the same direction, and then the maximum length would be n. But with this kind of condition, you can't really do that. So what's the best you can do? And Konyagin showed that the answer, well, Konyagin gave a gave a bound, and then Alon gave a matching construction to show that the answer is n to the 2/3 in this case. And Erdős heard about this, and then so he decided to ask another really natural question, maybe even simpler. Um, this one cares about the dimension. So what's the maximum number of vectors in RD, D-dimensional Euclidean space, with the same property? So among any three, some pairs orthogonal. And in 81, Rosenfeld answered this question and showed that the answer is just 2D. So that's very nice. We know that. But Erdős wasn't satisfied, of course. So he asked the more general version. What about if among any k plus 1 vectors, some pair is orthogonal? Is the answer k times d? Why k times d? Well, um, think about even why 2D even, because you can imagine if you have an orthonormal basis and you just take, you know, it and its negation, or if you allow vectors to repeat, then you can even take two copies of it or something, or two different orthonormal bases. So the answer in that case shows that it's 2D. And if you just do the natural generalization of this, you take k copies, you would expect that the answer might be KD for this more general problem. But as it turns out, Furedi and Stanley showed that no. Um, they found, an example for some specific K and D where it's KD plus 1. So it's a counterexample, but not a super strong one. So they wondered whether the answer might still be some polynomial in k times d. And finally, Alon and Szegedy said, no, in fact, you can have way more than that. So if you imagine k is fixed, then you can have d to the roughly log k many such vectors. And this was, I guess, pretty surprising. So, okay. And now I want to talk about,
Igor,
yes.
just for some reason, people see on the screen some kind of red.
Oh, yeah. I actually noticed this too. So there's some kind of issue where I don't see my mouse, and maybe for some reason it caused this issue. I can try to reset it,
Can
but
you
it's,
reset it maybe? Because I thought that it will switch when you start moving.
yeah, this is very strange.
Yeah, maybe then don't use this mouse to mark anything because somehow.
The problem is that for some reason I can't exit full screen mode. That's what I was having an issue with earlier. And the only solution I found was to stop sharing my screen. I literally have to figure out where my mouse is implicitly. It's really annoying.
It's okay, but maybe start sharing
Yeah.
again, and maybe let's.
Okay.
We understand that it's maybe annoying that you cannot point it, but then maybe having the scribble is
No,
also.
I understand. That's not even the issue. The issue is it's even hard for me to do anything. Okay. I have to stop the screen sharing from happening. This is actually incredibly frustrating. I'm sorry, guys. It's never happened to me before. Wow. Hmm.
Can you stop screen
I
sharing?
literally can't, like, my
So I can
hotkeys
maybe
do
do
not
it
let me do
manually.
it. This is just ridiculous. Um, okay. Um, God, don't know how to do this. I barely got it done last time. You know what? I don't have a better solution than
I stopped it. Don't worry. Right.
okay. This is maybe I should log out and log back in because I don't see another way to fix this.
But
Okay.
now you can share a screen, no?
Okay, this is good. All
Yeah.
right.
I just manually did it.
Okay, maybe this
Don't use your mouse.
all right. Let's try this one more time. Okay. You see my screen? There's nothing weird
Yes,
on it.
nothing is here.
All right. Okay.
Yes.
All good.
Right. So
Let's continue.
perfect.
All right. So now I want to discuss some nearly equivalent questions and some answers to them based on what I just talked about. So for that, we need some definitions. So the setup will always be that we're working in some Euclidean space with some inner product, and we have a graph with vertex set and edge set denoted by V and E. And so in the title, I said orthonormal representations, right? So here's the definition of that. So it's orthonormal representation is an assignment of a vector to each vertex in the graph with the property that they're all unit vectors, and crucially, for any two vertices such that they don't have an edge between them, the inner product should be zero. So with this definition, I can define the minimum semi-definite rank of a graph to be the minimum D such that there is an orthonormal representation by vectors living in D dimensions in RD. And so with this definition, a question that I studied together with Shoham Letzter and Benny Sudakov, is what is the minimum possible value of the minimum semidefinite rank over all H-free graphs with n vertices? And so how does this connect to what I was talking about just now? Well, in particular, if H is a triangle, then the previous slide said the previous result of Rosenfeld implies that the answer is actually ceiling of n over 2. And the reason is just because what it means to, have an orthonormal representation of a graph that doesn't have triangles, it means that for any three vertices, the corresponding vectors, at least one of the pairs needs to be orthogonal because at least one of the pairs needs to not be an edge. So great. So that's the question, and you can also ask it for other graphs. And one thing that we showed is that if you forbid a cycle of length k plus 1, then the answer is n over k. And so this is kind of the answer that Erdős wanted, if you think about it. But I guess you should have asked a different question then. I mean, indeed, when you have a triangle, there's kind of two natural ways to generalize it. One is to larger cliques, and another is to larger cycles. So for cycles, we understand how it works. And the construction that I mentioned of Alon and Szegedy in this language implies that the answer to this question is at most n to the roughly 1 over log k when h is the complete graph. And so the result that I wanted to talk about today and is that the same is true if H is a complete bipartite graph with parts of size k. So it's a generalization. This is a stronger statement. In fact, it implies the Alon Szegedy construction. So okay, I guess now you might say to yourself, cool, but maybe why should we really care about this particular variant of the question? So let me try to convince you why you might care. So for that, we need more definitions. So the Lovász theta function, and this function has many different definitions. I'm just going to give my favorite here, and later on we'll see another one. But since I wanted to use orthonormal representations, it made sense to use this definition. So it's the maximum over all orthonormal representations of the complement of G bar, of the largest eigenvalue of the corresponding matrix, which is the matrix of all the pairwise inner products between the vectors. So why is it G bar as opposed to G? Well, this is just a consequence of how Lovász defined it in the first place, and he had a particular reason for it. And, I always think about it as kind of, it should be G instead of G bar. So as long as you're consistent, it's okay. But I think Lovász himself has said that the most complicated thing about the Lovász theta function is knowing when to work with G or its complement. So that's easy to make a mistake with this. Okay, so now that we know this definition, another natural question you can ask, and something that we also studied, is what is the maximum possible value of theta of G bar over all H-free graphs with n vertices? So why am I saying theta of G bar here? Because this is really the quantity I want to think about. And it's, if you like, I think of it as kind of a vector chromatic number. In fact, we will see there is such a thing called the vector chromatic number later. And this theta of G bar is sometimes also called the strict vector chromatic number. So, okay, whatever. Here's the question. So what can we say about it? What is known? So one thing that's known is that when H is a triangle, the answer is n to the 1/3. That's how large the theta function can be. In general, the theta function is up to n. So this is and this again follows. It's almost equivalent to. It's not exactly the same question as the one that Lovász asked, but it's very similar. when the answer happens to be a vertex transitive graph, there it's literally the same question. Well, up to one other thing, which is that, when I talk about these orthonormal representations, I'm allowing different vertices to get mapped to the same vector, while in the original questions, the vectors all had to be distinct. But somehow, for all the things I'm going to talk about, it's not so important, this distinction. So don't worry about it so much. So, okay, we got the triangle. What else can we do? So again, another thing you can do is to look at forbidding a larger cycle. And what we showed is that for any cycle of length k, the answer becomes at most n to the 1 over k, which is nice. And it was interesting that the odd and even cycles did have somewhat different proofs. Um, we actually proved the odd cycle case first, but in hindsight, maybe this even cycle case is easier. And there's kind of some evidence to that based on another approach for a different problem, which maybe I'll get to. Anyway, so that's an upper bound, but what about lower bounds? Well, it turns out that this bound is tight if k is odd or if k is equal to 4, 6, or 10. So I guess you might wonder what is it about 4, 6, and 10, or maybe you already can guess. The reason is that for 4 cycles, 6 cycles, and 10 cycles, there exist optimally pseudo-random H-free graphs, which are extremal for the Turan number problem. So we know that these graphs have as many edges as they possibly can while being free of the given cycle length. And also, these graphs happen to be optimally pseudo-random, which means, which just I'm saying is that the maximum of the second and last eigenvalue is at most on the order of square root the degree, and they're regular. So that's the smallest you can hope for. So they're kind of as small in the sense as you can get, and it's known that this quantity, this maximum, is very much a measure of the pseudo-randomness of the graph. So that's why optimally pseudo-random. And of course, if you could find other graphs for which you have, uh, some kind of pseudo-randomness, then it can also lead to maybe a good construction. So, I mean, we don't know of one for C8 or other things, but it's interesting. And also, why is this bound tight for odd cycles? Well, that's because of a generalization of Nogus Alon's construction, which is pretty well known, I think. But anyway, okay. So what did we do? So okay, before that, I kind of the natural thing also to ask is what happens if you forbid a clique, right? So that's a harder question. But Feige actually gave a good bound. He showed that uh, the answer is at least n to the roughly 1 minus 1 over log k. So very close to n. Um, so he gave a construction when h is the complete graph on k vertices. And there's also some kind of upper bound, which I'll mention maybe at the end of the talk, but it's not so important. So I kind of want to point out here that when H is a complete bipartite graph, and if you have an optimally pseudo-random H-free graph, then at best the best kind of bound you can hope to get from this construction is on the order of root n. That's just a consequence of the lower bound for theta that it gives. And on the other hand, for the complete graph, we're getting something that's almost n. So question that we had that we didn't answer is if H is a complete bipartite graph with parts of size k, then is the answer closer to root n or close to n? So we didn't know. And it's kind of unclear because, for, well, I think that makes sense. And so a consequence of the result that I mentioned earlier is the construction I mentioned earlier is that the answer is at least on the order of n to the 1 minus roughly 1 over log k. Um, so that answers that question. So that was kind of the original reason why I did this construction. But then afterward, I found out that there are other interesting connections. So it's even more interesting. And how does that result imply this one? Well, you just need to use two simple facts. One is that the theta function of G is always at most the minimum semi-definite rank of G. And also that theta of G times theta of G bar is always at least n, the number of vertices. So Lovász proved both of this in the paper where he defined this function. All, and so it's easy to see from that that the theta function of G bar is at least n divided by the minimum semi-definite rank. So if the minimum semi-definite rank is very small, then theta is very large. So that's why we have this result. Okay, so going on. Okay, so enough about vectors for a second. Let's talk about just a purely combinatorial question, and then we'll connect it. So MaxCut. So of course I have to give a definition, but everyone here should know what this is. If you have a graph, then the MaxCut is defined to be the maximum over all ways of partitioning the vertices into two parts, A and B, of the number of edges between the two parts. So in general, it was shown by Edwards, and perhaps there were some other people that worked on it. I'm not sure if he was the only one to get this result. He got the kind of best version of it, but anyway, he showed that if you have a graph with m edges, you can always find a cut of size at least m over 2 plus a little bit, plus square root m. So first of all, why is m over 2 kind of the reasonable thing you would expect? Well, maybe you see it in an undergraduate combinatorics class, but if you just pick the parts uniformly at random, right, you flip a coin for each vertex, which part it goes to, then each edge has a probability of 1/2 of having one vertex in one part and the other in the other. And so the expected number of edges you're going to get in the cut is exactly m over 2. And so by probabilistic method, you always get at least that. And if you're more clever with how you do things, you can also squeeze out an extra root m from this. Kind of makes sense, at least intuitively, from the point of view of this random variable has some standard deviation. Maybe it's on the order of square root m, although it's not just that simple. You do need to do something. But we'll see another proof of this kind of implicitly um, from a different approach. So, okay. Uh, in 2003, uh, Alon, Balla, and Benny asked the question of what is the minimum of MaxCut of G minus M over 2 over all H-free graphs with M edges. So this difference between the MaxCut and M over 2, we also call it the surplus. It's a lower order term, but it's an interesting quantity to try to understand in general and also for H-free graphs. And it turns out that actually Erdős and Lovász already studied this question when H is a triangle. So somehow they are everywhere. And again, kind of unsurprisingly, Noga answered the question when H is a triangle, and he showed that the answer is m to the 4/5. And the construction here is again the same construction as for the maximizing the Lovász theta function question or the Lovász question. And they also pose an interesting conjecture, which is still open completely, which is that for any fixed graph H, there should be some epsilon so that the answer to this question is actually m to the 3/4 plus epsilon. So don't even, so why does this conjecture make sense? Well, to the best of my knowledge, the motivation for it came from the fact that for a random graph, you'll get the surplus will be on the order of m to the 3/4. So I guess if you forbid an h, you should hope to get a little bit better than that. Um, but it's not even known if you can get anything better than a half here. Like Edwards gives you a half, and for any fixed h, you can get a half plus epsilon. But to do something for a constant that's strictly bigger than a half, that's completely open. So that would be, I guess, a breakthrough if you could figure out a way to do that. Okay, so that's the question. And Alon and Sudakov studied this question and showed that if you have an even cycle, then the answer is m to the k plus 1 over k plus 2, at least. So they gave a lower bound, but only for even cycles. And then more recently, like good amount more recently, Glock, Janzer, and Sudakov showed that the same holds also when you have an odd cycle. So this is what I was referring to earlier, that somehow even cycles and odd cycles are different. And as you can see, the odd cycle case was done later because it was in fact more difficult. Um, and even more recently, together with Janzer and Sudakov, we showed that there's a pretty simple lower bound for the surplus that comes from the theta function. So that's how we connect everything here. So basically it says that the surplus is on the order of, is at least on the order of m, number of edges divided by theta of g bar. So if you can show that theta of g bar is small, then you get a large cut. And since that's what we were interested in is bounding the theta g bar from above, um, in a previous work, perhaps we thought we could use this to reprove in a different way the known lower bounds from the MaxCut. And indeed, so a corollary of this theorem is that, and of the previous results that I mentioned for cycles, is that the answer is what you expect for any cycle of length k. And I think the proofs were fairly succinct, and the proofs that were used by the previous authors, the first two answers I wrote here, were done using the probabilistic method and dependent random choice, while this is all using this one theorem basically. So if you're paying attention, you might ask like, well, the question we studied was the theta function for graphs on n vertices, and we wanted answers in terms of n. But now I'm asking you for something in terms of number of edges. But it turns out that if you have bounds in terms of the number of vertices on the theta function, you can also get bounds in terms of the number of edges. So this all goes through. Okay, so that's the result. And I wanted to give a quick proof of this result because it's really simple and everyone should see it. So for that, I'll need a different definition of the Lovász theta function, and it's another very useful one to keep in mind. So uh, again, we're assigning unit vectors to the vertices, but now I want to do it in such a way that whenever I have a non-edge in my graph, the inner product between the corresponding vectors should be negative. In fact, as negative as possible. So formally, the definition is it's the minimum kappa such that the inner product of any two such vectors, whenever there's non-edge, should be negative 1 over kappa minus 1. So the smaller kappa is, the more negative this number is. So the bigger the angle is between the corresponding vectors. And now with this in mind, the proof idea, well, actually, it was first used in the context of this problem by Carlson, Kola, Lee, Mani, Sudakov, and Trevisan, But this technique, it's called the random hyperplane argument. It's been well known in the CS community and in general for quite a long time. Um, so the idea is that if we know that our vectors have a big angle between them, then if we choose a random hyperplane and partition the vertices according to which side of the hyperplane they fall on, we might hope that they're more likely to fall on opposite sides, which makes a lot of sense. And so we might be able to win a little bit over the m over 2 bound that is trivial to get. But so let's see how that works. So suppose we have two guys, f of u and f of v. These are two vectors. And suppose we're just in 2 dimensions, but actually we can always reduce to this case because when you're choosing a random hyperplane, you're really, one way to do this is you just choose a uniformly random normal vector. And figuring out which side of the hyperplane you fall on is just taking an inner product. And inner products only care about the space, the subspace you're living in. So we can just always reduce to working in this 2-dimensional subspace. And so the question is, what is the probability that the edge UV falls on different sides? That's the chance that this hyperplane, which I just drew as a white line here, cuts between the two of them. So here's a little animation of it, the possible places it can be. And you can just calculate explicitly what this will be in terms of the inner product of the two vectors. And it will be exactly 1/2 plus 1 over pi times the arc sine of negative the inner product. You can work it out for yourself that that's what it is. And now we're basically done because the idea is that, well, arc sine of the thing inside the arc sine is a positive number, so arc sine of that thing is at least that thing, right? Sine of x is at most x, so that's the same inequality. And so we get at least 1/2 plus this factor of negative the inner product. And now if you just take so then the expectation, the expected number of edges will just be the sum of all these quantities. So that's how you'll get your m over 2 plus the m divided by the theta function. Because remember, the theta function is exactly defined to be, roughly the -1 over, like it's kappa, where -1 over kappa is this inner product. So it makes sense. If you have any questions, of course, you can ask me, but I hope it's clear enough. So that's it. That's the whole proof. Simple enough. And let's see. Since I do still have time, I'll also mention that I don't want to spend too much time on this. I know it's a lot of definitions, so please don't think too hard about this. But there is something called the vector chromatic number, and how it's kind of a very related thing to the theta function. So if you saw the definition from the previous slide, it's basically kind of the same thing, except instead of having equality in this inner product, you have an inequality. So whenever I have an edge, my inner product should be at most -1 over kappa minus 1. And now I'm not working with G bar anymore, because now this is really the right thing. So theta of G bar is an upper bound for the vector chromatic number, because again, theta of G bar can be thought of as like a strict version of the vector chromatic number. You're asking for more. So okay. So I'm mentioning this parameter just because, of course, the same argument gives a slightly more general theorem, which is this one. And it's not so hard to see. But another thing you can show, and this is something that I showed because I needed it, is that there are some lower bounds for the vector chromatic number in terms of say, the theta function and also the minimum semi-definite rank. And this is useful because it shows that also for the vector chromatic number, just like for the theta function of G bar, there is, if you're H free, where H is the complete bipartite graph, then there exists a graph so that the chromatic number, vector chromatic number is at least square root m minus a little bit. And so why is this uh, sorry, why is this relevant? Well, because, the interesting thing would be to try to prove this conjecture of Alon, Krivulevich, Bolobash, Krivulevich, Sudakov, using this theorem. But unfortunately, if you're trying to forbid even a complete bipartite graph, this will not work. So that's one other reason why this construction that I'm talking about is interesting, because it gives you a negative result. It shows you that unfortunately you cannot just use this theorem to prove that conjecture, sadly. And I'll just mention for 2 seconds that when we posted this paper on arXiv, we got an email from Clive Elphick, who did some calculations, like tried some graphs out from some database, and he saw that for some reason this surplus was actually always at least not just 1 over pi times this m over chi vec thing, but really 1/3. So that was a conjecture he made. And I just find it a little bit amusing because, pi equals 3 is a meme or something. But mostly, I mean, it won't affect anything for what we care about. But I do think it's an interesting question, because if that's true, then what would be the argument to prove it, right? It would be something more clever than just a random hyperplane argument. And I'm actually inclined to think that it's not true, but I just ask it anyway. Okay, let's switch gears for a second here. And this is kind of the last thing I want to talk about. And I promise again it will connect. But if you've lost track of what I've been saying, then you can reset here and start again. So now I want to talk about extension complexity of polytopes. Okay, what is this? So here's a definition, but instead of a definition, a picture is better. So imagine you have a polytope, and it's the projection of some bigger polytope, some higher dimensional polytope. So P is my original polytope. In this case, it's the hexagon, and P prime is the thing that you project from P prime onto P, onto a subspace, and you get P. And so the extension complexity of the hexagon is the minimum number of facets that this P prime can have, such that this P prime, when you project it, you get P. So in other words, in this case, if you count the number of facets or sides of the three-dimensional guy, it's 5. So this is implying that the extension complexity of the hexagon is at most 5. And why is this an interesting quantity to study? Well, in a lot of applications, when you're working with a polytope, you want to do some kind of optimization. And a lot of algorithms work based on the number of faces. And so if you could find some higher dimensional, perhaps polytope with much fewer faces, then you might be able to much more efficiently compute some quantity, assuming that, you can always pass to the projection and everything works out. And so how do I even know about this notion? Well, it's because of a result of Matthew Kwan, Lisa Sauerman, and Yufei Zhao. They showed kind of a curious thing can happen, is that you can find a polytope with at most n facets and living in only n to the little of 1 dimensions, but whose extension complexity is basically almost n to the 1 minus little of 1. So this shows that, you can't expect the extension complexity to always be something reasonable. It's sometimes gonna be as kind of as big as it can get. And I wrote there or vertices because this result also implies you have the same thing for at most n vertices by considering the polar dual of the construction. But anyway, so how does this connect to what I've been talking about? Well, let's try to get to that. So for that, I want to explain to you how we can even think about this extension complexity thing. It turns out there's a nice characterization. So, of course, any polytope can be defined by a collection of constraints. So I've written them there. So T constraints in this case, because any polytope is the intersection of a bunch of half spaces, and each of these inequalities defines such a half space. And I've written it in this way where all these numbers are at least zero, and I will call these numbers the slack. So this is some non-negative quantities. And one can define a corresponding slack matrix whose entries are the slacks, or the vertices. So the matrix is indexed by vertices of the polytope on the one hand, and the constraints, the set of constraints on the other hand. And so last definition of this talk that we will need is that if you have a non-negative matrix, that is a matrix all the entries are coordinate-wise at least zero, then its non-negative rank is just the minimum R such that you can write it as a sum of R many rank 1 matrices who are themselves non-negative. So this is, if you remove the words non-negative here, this is just the usual definition of rank. Okay, but finally, with this definition, I can state a really nice theorem due to Yannakakis, which is that the extension complexity of any polytope equals the non-negative rank of any slack matrix of it. So that means that for this purpose of understanding extension complexity, you just need to understand this non-negative rank of this corresponding matrix. And it also means that if you were looking to make constructions, then you basically need to construct matrices that are non-negative with some interesting properties, like the rank is small.
So Igor,
So
can you
yes,
Yeah.
clarify this slack matrix? So again, you have a polytope described by hyperplanes. Then the slack is just everywhere where these things are not equal, right? Or what?
Well, the slack could be zero, but for each vertex, I mean, for any point in the polytope, it's gonna, okay, this, I was a little bit imprecise, so I understand your question. So specifically, imagine that V is a vertex of the polytope, then it's like this quantity will be at least zero. Sometimes it will be exactly zero when you have the hyperplane which actually touches the vertex, but it sometimes not.
Okay.
And so now you imagine a matrix where you have all of these numbers written down, indexed by the vertices on the one hand.
Vertices versus planes.
Yeah,
So it's
exactly.
not a square matrix.
No,
Okay, so
but it can be if you want. But yeah, it's not in general a square matrix.
so then do you make it square? Do you multiply it on its transpose or?
I mean, I don't think in this definition, you didn't need it to be square, right? So the non-negative rank is still well defined for non-square matrices. But in the example I have, it will be a square matrix, so we won't worry about this.
Okay.
But yeah, in general, it doesn't have to be. And you can have like there's more than one description of a polytope in terms of these kind of inequalities. So there's many ways to write down this slack matrix. Okay, so anyway, going back to the to what I wanted to say is that finding a matrix which has large non-negative rank but small rank would be kind of the thing to do if you want to find a polytope with large extension complexity but living in a small dimension. So actually, this was already a question asked by Hrubesh. Perhaps because of this motivation, I'm not sure why he asked it. But the question is, what is the maximum ratio between the positive rank, the non-negative rank, and the rank over all non-negative n by n matrices? And so really, this is the question that we're going to address, and also the one that Kwan, Zarman, and Zhao addressed. So what they showed is that the answer to this question is at least n to the 1 minus log n divided by root log n. So very close to n. This is this little of one term that I said earlier. And a consequence of the construction that I mentioned that I've been talking about this whole time is that the answer is at least n to the square root log n over root log n. So of course, this improvement over their result is very minor. Um, in some sense, I just think of it as another way of doing their construction because their construction also is similar flavor to the one that I said, but it is this result is a bit better. Um, so let's see how could you prove this? This is the last thing I want to say, and um, oh, sorry. So I want to give a proof sketch of this. So the idea is, okay, there's one more kind of fact you need to know is that for any non-negative matrix, like we need some way of lower bounding this non-negative rank, and there is a nice combinatorial way to do it. The non-negative rank is at least the minimum number of rectangles whose union is exactly the support of M. So I hope that makes sense. So these rectangles cover everything that's in the support, but nothing else.
And support is what's not zero, right?
Yes, yeah. And in our case, it will be where the edges are. So yeah, exactly. So okay, so now what matrix am I going to take? Well, of course, the Gram matrix of an orthonormal representation of H-free graph which where H is the complete bipartite graph of parts of size K. And in particular, I will take the construction that I know I have that where the dimension of the representation is very small. Okay, so now what's the idea? Well, the point is that if you take any rectangle that's completely in the support of M, then I claim that it has to have cardinality at most 2 times K times N. Why? Well, if you think about this rectangle, if both its like length and its width, well, so a rectangle here means just any, you know, subset of the matrix indexed by some subset of the rows and some subset of the columns. So if both of these numbers were bigger than 2k, then I could find within them disjoint sets of size k in both parts, so that you would have all the edges being there. But that would be a complete bipartite graph with parts of size k, and I don't have such a thing. So for sure, at least one of the two sides needs to be size at most 2k. And the other side length, I have no control over, but the whole matrix is going to be n by n, so the other side length is at most n. So the number of entries in the rectangle, its area is at most 2k times n. And therefore, because of what I told you guys, that this rank, non-negative rank, is at least the min number of rectangles you need whose union covers the support of M, it follows that the non-negative rank is at least M, the size of the support, or equivalently the number of edges, divided by this 2kn thing. And basically, the idea is that k will be like on the order of n to the square root log n divided by square root log n. And so, and m will be almost n squared. And so this non-negative rank will be almost n, like n minus this square 1 over root log n thing. So that's like the optimal choice. And that's it. I mean, from here I mean the rank of the Gram matrix is going to be the rank of the representation, so you get a large ratio this way. I hope that makes sense. Okay, so that's basically all I want to talk about. And now I will just finish off by kind of recapping and asking some questions of what else can we say? So, of course, doing answering any of the aforementioned questions for some new types of H that were not previously known would be interesting. And there has been some work in that direction, um, even recently, like within the last 6 months, maybe year. Um, but okay, so if I let Fn be the family of all H-free graphs, where H is the clique of size k, then to summarize what we know is that the minimum semidefinite rank, the minimum of the minimum semidefinite rank, lies is at most n over roughly 1 over log k. And we also know that there's some kind of lower bound. We proved this lower bound, but it's really not so great. So the best lower bound we have is just n to the 3 over k. And there's a huge gap there, so I don't know. I assume the lower bound is wrong. That's my guess, but I'm not sure. And similarly, we also have the lower bound for the maximum of the theta function of g bar of n to the 1 minus 1 over log k. This is like the Feige construction. And also a similar thing follows from our stuff. And there's also a matching, I mean, there's also an upper bound due to Noga and Kahale, Noga, Alon, and Kahale. And again, as you can see, like there's a big gap in the sense, I mean, it's not, maybe it doesn't seem like a big gap, but again, there's a difference between this log k and just k. So I would like to know what is closer to the truth. And I'm tempted to believe that the construction is more likely to be closer to the truth because the bounds, the way you prove these bounds, it's kind of very simple, and I suspect it's not optimal. Okay. Also let F sub m be the family of all H-free graphs with m edges. So now we're indexing based on number of edges. So there's a conjecture also of Alon and Sudakov that this minimum possible value of the surplus over all such graphs is going to be m to some constant. So there should be some constant such that the answer is like this. And this is open. So for some graphs, we know the answer to that there is a constant and what it is, but the only way we know that there is a constant is by actually showing explicitly what it is. So it would be great if there was some kind of abstract argument that could imply that this constant exists without knowing what it is. Uh, oh, sorry. And of course, the most interesting conjecture here, I think, is the one I mentioned before, which is that this constant should always be bigger than 3/4 for any h. And of course, it should be clear to you guys, but in case it isn't, this question was asked over for all h, but really it's enough to think about complete graphs. And yeah, there was also this conjecture of Elphick. And the last thing is that this construction that I mentioned gives this nice lower bound for the ratio of the non-negative rank to the rank. But as far as I know, there are no known upper bounds that are better than like n. I don't even know if there's like n over 2. Maybe there's something like n over 2, but it would be very interesting to find any kind of non-trivial upper bound for this quantity. And with that, I think I will finish my talk. So thank you.
Thank you, Igor, for the nice talk. So questions? So actually, I have a question. So if you go back to your slide, the last slide of the questions, I mean, getting n over some constants should be easy, right? Because the rank plus is at most n, right? If the matrix is semi, that is the orthogonal, I mean, just the composition into eigenvalues. So then you're just telling me that the rank should be at least something, right? A number of non-zero ones. So, right? So it's like, so the, right? So what you should get like easily here?
So I guess I cannot rule out that there's like some matrix of rank 10 which has I mean, okay, so I believe that you could maybe get n over a constant this way, but I guess I cannot rule out that there's some matrix of, say, rank 10 whose non-negative rank, it's n by n, and whose non-negative rank is like n to the, like n over 100 or something. I that sounds impossible, but again, I haven't spent too much time on this question, but I asked Matthew also about it, and he said it would be interesting to find any bound better than n. So I think as far as he told me, it isn't known. But rather than take my word for it, I would also look in the literature because I haven't, looked at every paper related to non-negative rank. But yeah, I think it's a cute question.
More questions, please.
Hey, Igor, do you have any suspicion of the answer of cycles, like the surplus?
Well, I mean, I kind of suspect, okay, I mean, it's tied to the Turan problem in quite a strong way. So for odd cycles, we know the answer. And for even cycles, well, if there are these optimal Turan constructions and they happen to be also optimally pseudo-random, then the answer would be that. But I don't know if those exist, but that's the real question, perhaps.
Okay, okay. So the surplus is known for all the odd cycles. Okay, okay.
Yeah, like asymptotically the C of H is known for odd cycles.
Okay, okay.
Just because luckily this construction of Nova generalizing, it's given. Yeah.
Yeah, exactly.
More questions? So if not, thanks Igor again. Right.
Thank you.
Thank you again for a nice talk and effort to giving it. So I hope to see you all next week. So it will be taught by Julian Sachas-Budhe. And I sent the announcement and the abstract in basically today, tomorrow. So we can stop the recording.